Hello, my name is Kim Espejo and this is my final video. To start the identification of my structure, I will begin with MS spectrum. First, identify the M+, which is going to be at 94. Next, identify the base peak at 45. Next, I subtract the M+ from the base peak, so 94 minus 45 to get M minus 52. Next, I'm going to calculate the degrees of unsaturation using the formula. The DOU formula is 2 times the number of carbon plus 2 plus the number of nitrogens minus the number of halogens minus the number of hydrogens, all divided by 2. The chemical formula for my structure is C3H7OCl. So my DOU equation is going to be 2 times 3 plus 2 plus 0 minus 1 minus 7 divided by 2, and the DOU is going to equal 0. Mass spec will usually give you the chemical formula, but you can also calculate it by doing some calculations from the spectrum. So I'm going to take 94, which is the M+, subtract that by 35, which is the molecular weight of chlorine, to get 59. Next, I'm going to subtract that by the molecular weight of oxygen, which is 16, to get 43. Next, I'm going to take the molecular weight of carbon, which is 12, and divide that by 43 to get me the number of carbons I'm going to have, which is 3. Next, I'm just going to calculate the remainder to get me the number of hydrogens I have in my formula, which is 7. Next, we're going to look at the IR spectra, and first we're going to identify the different zones. This is zone 1. It ranges from 3,700 to 3,200. Next is zone 2, which ranges from 3,200 to 2,700. Next is zone 3, which ranges from 2,300 to 2,000. Next is zone 4, which ranges from 1,850 to 1,650. Finally, we have the last zone, zone 5, which ranges from 1,680 to 1,450. Next, we can use this infograph to help identify the different functional groups present in our molecule. And it also goes by range, and then you just match up the peaks with what you have on the IR spectra. So on our spectra, it looks like we have an sp3 in zone 2, and then it might also look like we have something in zone 5, but according to the infograph, this area is going to be like the fingerprint region. In the other zones, it looks like we have nothing. Alright, next we will go to proton NMR, and from our data it looks like at 3.3 we have a singlet with an integration of 3, and then at 3.63 we have an octet with an integration of 4, and this little octet is actually abnormal, and once we draw the structure I can explain why. Okay, so we can also use an infograph to help identify the environments. So again, the chemical formula for this structure is C3H7OCl. So I'm going to draw a possible structure here, and then we will go ahead and identify the different environments. I'm going to go ahead and draw in the hydrogens to help visualize a little better, and then I'm going to circle the different environments that I think is present in this structure. Alright, so here are the 2 different environments that I think is in the structure. On the right side, I'm going to match it up with the singlet, and on the left one, I'm going to match it up with the octet. Now to prove this, we can do the N+1 formula. Okay, so the N+1 rule is just going to be N, which equals the number of hydrogens the environment of hydrogen sees, and so it sees 0. So it's going to be 0 plus 1 equals 1, and that 1 is going to equal 1 peak. So I'm going to match it up with that singlet because it's a single peak, and we see that there's 3 integrations. And so in this environment, there are 3 hydrogens, which is going to equal the 3 integrations we see in the spectrum. For the left environment, it's going to be a little bit tricky to prove because it's an octet. And the reason it's an octet of peaks is because of how electronegative the 2 elements next to the 2 carbons are. So chlorine is extremely electronegative and oxygen is electronegative as well. And it's going to cause the peaks to split more and make it into an octet. But we see that there are still 4 integrations and there are 4 hydrogens in this environment. So it makes sense to see that splitting pattern, but also that integration of 4 for this set of hydrogen. Okay, finally we're going to look at CNMR, and the first thing I do is label the peaks in this spectrum 1, 2, and 3, and then try and match it to the structure. So for the peak I labeled 3, I'm going to match it up with the carbon closest to the most electronegative element, which is chlorine. For peak 2, I'm going to match it with the carbon next to the carbon and the oxygen. And then for the peak 1, I'm going to match it up with the carbon that has the 3 hydrogens and then the 1 oxygen connected to it. Alright, so we can also look at an infograph to determine the different environments of the carbon in our structure. So for the peak I labeled 1, it was at 42.6. We can match it up to a primary alkyl. And then for the peak I labeled 2, which is at 58.8, we can probably match that up to a secondary alkyl. And then the other one doesn't really fall into place, but we can see that how electronegative it is. It could be closest to the chlorine. In the end, this is what our structure should look like.